that's different? I hope you said that what's different is that there's an x squared term. In the past, all our x terms were simply linear, just x. Here we have x squared. What are we going to do? Well, we could cry. That would be kind of silly. Or we could go to the visual and see exactly what we're doing, which is the same thing, finding the y-intercept. Wait a second. When we replace x with 0, we get the square root of negative 16. That's imaginary. It's 4i. But the fact is, being imaginary, it doesn't appear on this graph paper, which means there is no y-intercept. Is that terrible? No. It's just what happens in this particular function. Then what do? We seek out the x-intercept. Well, the x-intercept is obtained by setting the function equal to 0, and we have the square root of x squared minus 16 equals 0, and that's highlighted. And then we solve that, we get plus or minus 4. Remember, because we're solving x squared equals 16, and we're taking the square root of both sides of the equation, both sides, we get the plus or minus answer. Plus or minus 4, so we have two x-intercepts, 4, 0 and negative 4, 0. Well, the next thing to do is to look at the endpoints. And the next visual will show us how to do that. And simply we take what's inside the square root, set it equal to 0, and you'll notice we get the same points as we had for x-intercepts. Those points are sketched on the graph at the bottom of the visual. But the problem is, are you prepared to draw a curve right now with 2 points? I don't think so, and in fact, we have no idea what happens. We know that this curve does not cross the y-axis. How do we know that? We know that because there's no y-intercept. So what we need to do is plot some points. So in case of in the past we said we could plot points to help us feel secure. Now we need to plot points to figure out what is going on. The next visual shows us how we plot some points. We just picked an x. The x should be selected so that when you square it and subtract 16, we get a number that we can take the square root of. For example, if we put in x equals 6, we would have gotten 36 minus 16, which is 20. The square root of 20 certainly is on your calculator, but it's an approximation. It's certainly not a whole number. I chose 5 because 5 squared minus 16 is 9, and the square root of 9 is 3. We also put in negative 5. Negative 5 squared is 25, minus 16 is 9. So when x is negative 5, y is also 3, the square root of 9. And we've plotted those 2 points. And notice what we have. We have 2 curves, if you will. And in fact, if you turn your head sideways, these 2 curves sort of look like one side of an up parabola and one side of a down parabola. And perhaps in your Algebra 2 course, although I won't be covering in these tapes, you might lightly cover something called conic sections. You will certainly do this later on in senior mathematics or college algebra or pre-calculus, and you'll talk about something called an hyperbola. And this is sort of half of hyperbola. Okay, so that was a little different, but again, by plotting points, we were able to figure out exactly what our curve looked like. All right, I think it's time to start looking at something just a little bit different. How can we, is there anything left? Yes, I think so. Let's go to the board and look at a very special circumstance. And that is y equals the square root of 9 minus x squared. Now, what's different about that? Well, it has an x squared, but that's not, we just had one with an x squared in it. It's that it's minus x squared. Now, that's going to change what the graph looks like, believe me. What are we going to do? The same thing. The x-intercept, when x is, let's start with the y-intercept first. The y-intercept is when x is 0, and when x is 0, y is 3, since the square root of 9 is 3. And then we're going to take a look at the x-intercept. We'll set this equal to 0. And we solve, we square both sides. And of course, 0 squared is still 0. We wind up with 9 equals x squared, or x equals plus or minus 3. Once again, we are taking the square root of both sides of the equation, so we get plus or minus. So therefore we have x equals 3, y equals 0, x equals negative 3, y equals 0. These points look a lot like this, but they're three separate points because, of course, this is 0, 3, this is 3, 0. Our next visual will show us the plot of those 3 points and the sketch of the curve. Notice it looks interesting. Why does it look interesting? What shape is that curve? Well, it's drawn, you'll notice, so it looks like half a circle. And it should look like half a circle because that's what it is, a semicircle. That is a semicircle whose center is at the origin at 0, 0. Notice the radius is 3 because 3, 0 is 3 units away from the origin. 0, 3 is 3 units away from the origin, and so is negative 3, 0. Again, if you feel uncomfortable with this, we could plot some points, but I'll be quite frank, the rest of the points you could plot would probably involve the square roots of non-square numbers. When you have 3 points and you see they're all the same distance from point, you probably have a semicircle, or in some cases, a circle. All right. Now, in the time remaining, we want to talk about cube root functions. Cube root functions are not quite as important, but let's take a look at how we solve them. How about the cube root of x plus 2 equals 3? We solve this the same way as we did the square root functions. We isolate the cube root, which in this case is already isolated, and instead of squaring both sides, we cube both sides. Because the cube of a cube root is what's inside. The cube of 3 is 27, and we get x equals, not negative, no. We're going to subtract 2, and we're going to get 25. And 25 plus 2 is 27. The cube root of 27 is 3. And that's a simple example of a cube root function. Let's take a look at the next visual, which gives us a cube root function. We've got to do a little bit of manipulation of numbers because we have the cube root plus 3 equals 0. We subtract 3 from both sides, and we cube both sides as is highlighted on the third line, and we solve, we get x equals negative 20. If you replace the x in the original equation with negative 20, we get the cube root of negative 27, which of course is negative 3. Cube roots, odd roots, can be taken for negative numbers and you get a negative answer. And of course, negative 3 plus 3 equals 0, so that checks. Now, let's take a look at the graph of the basic cube root function y equals the cube root of x. So let's go here to the easel. And just as before we looked at the square root of x, let's take a look at the cube root of x. Y equals the cube root of x. Obviously, we place 0 in there first. And when x is 0, the cube root of 0 is 0. When x is 1, y is 1. When x, let's see, we got to come up with another cubic number. X is 8. 1, 2, 3, 4, 5, 6, 7, 8. When x is 8, the cube root of 8 is 2. The next point will be 27, 3. That's off the easel. But remember, we can put negative numbers. Let's put a negative 1 in. The cube root of negative 1 is negative 1. And of course, the cube root of negative 8 is negative 2. 1, 2, 3, 4, 5, 6, 7, 8, negative 2. And what we have is something very interesting. We have a graph that looks like this, that is rising up, hits this 0, 0 in this case, and sort of turns over, and now almost looks like a square root situation. And I put little arrowheads on the end to indicate we're going to go on forever and ever. This I call the 0 point. It isn't always at x equals 0, but it is where the curve changes. In calculus, we call this an inflection point. Very interesting. And you'll notice if you turn this on its side, you'll get something that looks like the functions we investigated when we looked at polynomial functions, like the cube xy equals x cubed. All right, let's take a look at a sketch of a cube root function. The next visual shows us y equals the cube root of x minus 8 minus 1. And on the screen you can see the y-intercept is obtained, the x-intercept is obtained, the y-intercept is 0, negative 3, the x-intercept is 9, 0. We've plotted the points on the next visual, 9, 0, and 0, negative 3. Is that enough to graph a cube root function? The answer is no. We need what I call the 0 point, the point where the curvature changes. Well, how do we do that? Well, that occurred in our original graph at x equals 0. Let's see what makes what's inside the cube root 0. Let's go to the next visual. And the next visual shows us the original equation, y equals the cube root of x minus 8 minus 1. And we set what's inside the cube root, x minus 8, equal to 0. That's why I call it the 0 point. It's a lot like the endpoint in those square root graphs. We solve for x, we get x equals 8. But remember, this is a point, so we replace x in the original equation with 8, and we get y equals negative 1. Let's look at the next and last visual, which shows us an actual graph, or a sketch of the graph, using the 3 points. The x-intercept at 9, 0, the y-intercept at 0, negative 3, and this 0 point at 8, negative 1, where the curvature changes. You'll notice the sketch looks a lot like the one we did at the easel, the one that was y equals the cube root of x. It's just moved over and down. In perhaps some later course, you can look at what changes, what causes things to move to the right and left and up and down. So what we've seen in this lesson is that we can solve square root equations, but it's very important to check. We can solve cube root equations similarly, and obviously it's a good idea to check, but not as vital as with square root equations, because with square root equations, we sometimes get answers that do not check in the original equation. And graphing square root equations, we look for the y-intercept, the x-intercept, and the endpoint. Cube root equations, we look for the y-intercept, the x-intercept, and the 0 point, the point where the curvature changes. Hopefully, if you have this, if you don't, go back, replay the tape, and you'll be an expert at graphing and solving square root and cube root equations. Our next lesson, lesson 24, will cover exponential functions, something to look forward to.